All right, it's 9:05. Let's get down to business. 250. Okay, yeah. Anyway, so graphing this is going to help us do the second part. This is an absolute value function. It's pretty straightforward. It's the usual absolute value function shifted 3 to the right. So if I'm graphing this, trying to do as little work as possible, I'm just thinking of the bottom of my V over here at 3. I might also find the y-intercept. If I plug in 0 for x, I get 3 for y. So it's going to look something like this. And then like this. Since I know I'm going to use this graph to answer the second question over here, I might also figure out what's going on over at 7. If I plug in 7, the absolute value of 7 minus 3 is the absolute value of 4, which is 4. Just kind of using the fact that I know I'm going to use this graph to help me answer the second part of this question. So I want to find the integral from 0 to 7 of the absolute value of x minus 3. The way we're going to do this is not by trying to actually find any antiderivatives. We're just going to use the graph. I'm saying, okay, great. Well, this integral is equal to the area of that triangle plus the area of that triangle. So this integral from 0 to 7 of the absolute value of x minus 3 is going to be, well, this triangle over here has a base of from 0 to 3 is 3 and a height of from 0 to 3 is 3. So the first triangle has an area of 1/2 base times height. And the second triangle has an area of 1/2 its base, which is 4, times its height, which is also 4. And then we're going to get something. We're going to get 9/2 plus 16/2. Normally, I would reduce that to 8, but since I'm going to add those fractions and I've already got a common denominator, might as well just leave it as 25/2. Cool. I wouldn't be surprised at all if you saw a question like this on an exam. It's pretty typical to ask and to expect the answer to be done this way. There are other ways of doing this where you could actually like rewrite the function as x minus 3 between 0 and 3 and negative parentheses x minus 3 when x is bigger than 3 and then integrate both of those, but that's too much work. You want to do it the fast way. All right, lots of things to talk about today. Let's get started with integration by parts because if you're not there yet, you certainly will be there soon. So a note on integration by parts. Integration. And don't worry, we're still going to talk about U substitution. So integration by parts, which we usually abbreviate as IBP. So a note here is that this actually isn't always 100% true, but it's pretty much 100% true. Whenever you're considering using integration by parts, you're usually considering it for what we typically refer to as a mixture type of integral. So we're going to say that we use integration by parts for integrals that are quote unquote mixtures. When I say mixtures, I mean a mix of 2 types of functions. Technically, it could be 2 or more types of functions, but pretty much every time it's going to be exactly 2. So mixtures of 2 types of functions. Typically, if we see a mixture before we start using integration by parts, we should first see if we could have done a U substitution in the first place. So continue on here. There's a little more to say. So typically or usually, we have a mixture of 2 of the following things. You have maybe x to a power, like x squared, x cubed, x to the 1/2, any kind of power of x. You have the natural log of x, e to the x, or a trig function, sine of x, etc. Those are the 4 different types of things we mix together, usually. There is one other thing that sometimes enters the fray. So I would say this is any power of x. This is a log. This is an exponential. This is a trig. And then sometimes, unfortunately, we also get stuck with an inverse trig, which I would classify as being different. Sometimes inverse trig. like arctangent, arcsine, etc. So if you see two of those types of things in your integral, the first thing you should try, try U sub. Because U sub is just easy. And and typically both of these methods won't work. So either a U sub will work or integration by parts will work. And we should try to see if the easier thing will work first. And then if that doesn't work and it's a mixture, you should then try integration by parts. All right, then try. I'm going to say again, this is for when we have a mixture. I will also say when we have other integrals, we can still use a U sub. So like there's plenty of integrals that aren't quote unquote mixtures where we will use a U substitution, but there aren't really, it's a rare exception, integrals that aren't mixtures where we use integration by parts. So you kind of have to have two types of functions for integration by parts. As someone wrote in the reflection the other day, which I thought was really, really good, they learned that they can use a U substitution when there are composite functions and integration by parts when there are different functions multiplied together. And we'll kind of see that as we go along here. So I'll refer back to that. I thought that was really nice way of breaking it down. The reason I didn't anti-differentiate x minus 3 in that previous problem was because it was easier to find the area under the curve using just an area formula, because that's all a definite integral is asking for. It's kind of similar actually to how, let me just go quick aside here. Well, no, actually I won't do that. I'm just going to say that for now. That's why I didn't anti-differentiate it. So let's look at some, well, actually, let's talk about what the integration by parts process is before we start getting too far into here. So integration by parts comes from the product rule, which is why it's nice to think of using it when you have two functions multiplied together, because that's really kind of where it's coming from. So let's look at this briefly here. If we look at the derivative of the product of f of x times g of x, the product rule says that's going to be equal to f prime times g plus f times g prime. And then if we start anti-differentiating both sides, well, yeah, sure. The antiderivative of f times g prime should be equal to the antiderivative of f prime times g plus the antiderivative of f times g prime. But the antiderivative of the derivative is just the stuff you have. So this right here is just going to be f times g, and it's equal to the antiderivative of f prime times g plus the antiderivative of f times g prime. And then for whatever reason, we like to rewrite this so we isolate this. So we're going to rewrite this as the antiderivative of f times g prime equal to just f times g minus this part right here, the antiderivative of f prime times g. However, we don't usually use these letters when we write it because it just doesn't seem convenient to remember. So what we typically do is then we say, well, we're going to say that f of x is actually u and g of x is actually v, and f prime, we're going to call that du instead, like for the derivative, and g prime we're going to call dv, and we're going to rewrite this as the integral of u times dv equal to u times v minus the integral of v times du. Sorry, there's your du, there's your v. And this is our integration by parts formula. The whole point of this formula isn't that it actually calculates the integral for you. It's that it takes your integral or antiderivative that you're trying to find and re-expresses it as something that is typically easier to then anti-differentiate. That's the whole kind of point of this process. Let's look at some examples. Yeah. So let's look at, yeah. So we're going to actually kind of start off, we're going to backtrack a little bit. Is there a way to solve the second one? There is a way to solve it, and I'm happy to talk about that in office hours. But I would say you really, if you have an absolute value function you're trying to find the definite integral of, you really should graph it. So let's look at this integral. The antiderivative of x times e to the x squared. So some observations. Oops, terrible. I hate it. If you ever notice that little thing is like, if you notice that you're seeing all that, let me know. I think it looks terrible and I would rather not be there. So I'll click over there and it'll undo it. So I will say I have a mixture here, right? I have a power of x and I have an exponential or an e to the something. So when I have a mixture, what am I going to do first? I'm going to look for a u sub and see if I can get one. And here it's going to work. So here I'm actually going to be doing a u substitution. We're going to let u equal x squared because it's trapped in the exponent, and also its derivative is what we want it to be. Du dx is 2x, so 1/2 times du is equal to x times dx. And I can rewrite this integral. I can rewrite this as the integral of, let's see, my x times my dx is going to be my 1/2 du. So I've got 1/2 du. That has replaced the x times dx, so I no longer have to worry about writing any of that. And then I still have my e to the x squared, which is going to be my e to the u. I've completely rewritten my integral in terms of the variable u. Now I can anti-differentiate it. The antiderivative of e to the u is just e to the u. We have a plus c. And then finally, since we started off with the variable x and we're finding the antiderivative, we have to end with the variable x. So we're going to get 1/2 e to the x squared plus c, just replacing u with what it's equal to in terms of x. If you took the derivative of this, you would get 1/2 e to the stuff times the derivative of the stuff, which would be 1/2 e to the x squared times 2x, which would be exactly x e to the x squared. So the derivative of this is the function we started with, so that is the antiderivative. All right. No time for slowing down. So if you have questions, you should ask them, but I'm going to keep going as I try to not stop to say, do you have any questions? But you know me, I can't help it. So question.
Where'd you get the 1/2?
Where did I get the 1/2? So I have a du dx equal to 2 times x, but I don't have a 2 times x here. So what I did was I rewrote this, I divided or multiplied both sides by 1/2, divided both sides by 2. So that's where the 1/2 is coming from right there. It's from there. So then let's compare this with the integral of x times e to the 2x. Seemingly very similar, but not really at all. Here, if we tried to do a u sub, the only real plausible choice might be letting like u equal 2x, but that's not going to get us anywhere. U equals 2x. In fact, let's pretend like we did. Well, if I did u equal to 2x, my du dx would just be 2. So my du would be 2 times dx, or 1/2 du would equal to just dx. If I start replacing this, I'm really going to have almost the same integral left over. I'm going to have, let's see, my dx is equal to 1/2 du, so I've got a 1/2 du at the end. My e to the 2x is going to be e to the u. And my x that's still there, well, if I divide both sides by 2 here, u divided by 2 is equal to x. That's not super helpful. I've really essentially got the same integral I had before. I've still got a u times e to the u, or an x times e to the essentially x. So in this case, u substitution is not the way to go. So we're going to try and erase my parts instead. We have a mixture. So when you're trying to use an erase my parts, there's a pretty good algorithm for how we want to pick what we're going to have u equal to. So we're going to pick u equal to the first thing we see. Do we see a logarithm? No. Do we see any power of x? Yes, we do. We see x to the first. But if we didn't, then we looked for a trig function. If we didn't see that, we looked for an e to the x, although we almost never let u equal the e to the x part. So this acronym LATE is how we often pick what we're going to let u equal. So logarithm, any power, trig function, exponential. I will point out the reason for this is because when we pick our u, we want to pick a u whose, when we take its derivative, the derivative of that thing is simpler. So if you're picking u equal to x to a power, taking its derivative usually makes it simpler. If you're picking u equal to the trig function, often its derivative is going to be simpler. Whereas the thing we're going to choose for dv, the other piece here, should be something that when we anti-differentiate it, it doesn't get more complicated. That's why e to the x is often a really good choice for your dv, because its antiderivative is essentially the same. So here, we're going to pick u equal to x. And once we picked u, dv has to be the rest of the integral. So I picked u equal to x, dv is everything, including the dx that's left over. So dv is going to be e to the 2x times dx. Our du, the derivative of x is 1, so our du is 1 times dx. Our v is the antiderivative of e to the 2x, and this is why we spent some time talking about those mini substitutions. If I antidifferentiate e to the 2x, I'm just going to get e to the 2x divided by the coefficient of x there. So I'm going to get e to the 2x divided by 2, or if you prefer, 1/2 e to the 2x. So now we're going to rewrite our integral. Again, right, this doesn't complete the process. We still have more to do after we do this. So we're rewriting this as u times v. So that's going to be x times 1/2 e to the 2x. Let's actually write down what things are. So there's our u. There's our v. Minus the integral of v du. So that's going to be 1/2 e to the 2x times dx. And the point here is that this new thing that we're integrating should be easier to actually find the integral of. And it is. We can find the integral of that. So we're going to end up getting x times 1/2 e to the 2x, or I might rewrite that as 1/2 times x times e to the 2x minus 1/2 the I'm pulling out the 1/2 in front. The antiderivative of e to the 2x, we already did that work, is again 1/2 e to the 2x plus c. Yes, we could simplify this as 1/4 e to the 2x, but I don't think we need to spend the time writing that down. So there's an integration by parts problem. We rewrote it as this. So I'm going to say this probably more than too many times. We found our ultraviolet super voodoo. That's a thing people say to remember the formula here. You've got your UV, your ultraviolet rays, minus the integral kind of looks like an S, so that's your super. And then you've got your VDU, your voodoo, your ultraviolet super voodoo. I'll say it again. That's how I remember the integration by parts formula. Questions about this one? Yeah. So if we go back to if we look back here at how we derived the formula here, we took the product rule here and said the derivative the derivative of f times g is f prime g plus fg prime. So this is really acting like our f is like our u. Let me use red here. Our g is like our v. Our f prime is our du. Our g is our v. Our f is our u, and our g prime is our dv. And then we're just rearranging this in a way so that we've got our f and our g prime, that's our u and our dv, and we're taking the integral of that, equal to our u times our v minus the integral of our g, which is v, times our f prime, which is our du. So really what we're doing is we're just using this formula that is true. We're saying, okay, I've identified in my original integral the role of u and dv. So right here, this is my u, and this is my dv. And the formula tells us that the integral of u times dv is equal to our u times our v minus the integral of our v times our du. So in this case, well, our u was x, our v is the antiderivative of dv, which is e to the 2x divided by 2. Well, yeah. Kind of. It's the derivative. Well, it's the derivative of the piece we've chosen it to be, right? Like we have picked the e to the 2x is our e to the 2x times dx is our thing that's going to be dv. It's the no, it's definitely dv. So when you're doing integration by parts, you're definitely picking in the original integral what your u is and what your dv is, and then you're finding the other stuff to plug into the formula. So I'm going to ask over here, why do we write e to the 2x divided by 2? Well, because the antiderivative of e to the 2x is e to the 2x divided by 2. So if you think about this for a second, the antiderivative of e to the 2x dx is e to the 2x divided by 2, or 1/2 e to the 2x. Yeah, I'm not writing the plus c because the derivative of 1/2 e to the 2x is equal to 1/2 e to the stuff times the derivative of the stuff, which is 2. And then the 2 times the 1/2 becomes 1, and you just get e to the 2x. So whenever, I know we've said this a few times, but whenever you antidifferentiate e to the something times x, right, the antiderivative of e to the kx, where k is a constant, is just e to the kx divided by k plus c. Or if you want to write it as 1 over k times e to the kx. That's a fine way of writing it as well. And that kind of idea is true for any basic function we know how to antidifferentiate where you've multiplied x by a constant. Yeah, you could do a u sub here. No, you shouldn't. You should just be like, I can do this without doing the u sub. So another example is would be like the antiderivative of, say, cosine of 6x. We know the antiderivative cosine of x is sine of x, so the antiderivative here is going to be sine of 6x divided by 6. Because the derivative would make us multiply by 6. We'll see. All right, let's look at some more examples. So, yeah, let's look at the next one. Let's say we have, I'm going to change that one a little bit. Yeah, let's say we have the integral of the natural log of x divided by x. Again, I'll point out we have a mixture. We have a logarithm and x to a power. And before I try integration by parts, I'm going to try a u sub. And it's going to work. If I let u equal the natural log of x, my du is exactly 1 over x dx, which I have. So I can rewrite this as the integral of the natural log of x times 1 over x dx. And that's going to become the integral of my 1 over x dx is my du. I can't emphasize enough, I keep trying to, but I can't, how important it is to make sure you deal with the dx du change before you look at anything else. Notice how I'm writing this part first. I'm like, oh yeah, the 1 over x dx is my du, and then I look at the rest of the stuff in the integral. Oh, the natural log of x is just u. Yes, you could have written that part first, but I want to encourage you to do it the other way. Anti-differentiate u to the first, we get u to the second divided by 2 plus c. We plug back in that u is equal to the natural log of x. We get the natural log of x squared divided by 2 plus c. Versus, where'd you go here? The integral of x squared, sure, x squared, why not? Times the natural log of x dx. Now there's not a good u substitution. I pick u equal to the natural log of x, my du is going to be 1 over x, and that's not going to help me. So in this case, I have a mixture, but I'm going to try integration by parts. Okay. So what are we choosing for a u for integration by parts? Right, not a u sub, but we still, it's unfortunate that u sub and integration by parts both use the letter u, but it's just the way it's done. So here we're going to pick u equal to the natural log of x. We're doing integration by parts, and there's a logarithm. That is almost always going to be your choice for u. Also, because if you pick it for dv, the antiderivative of the natural log of x is something you actually have to use integration by parts to find. So it's not easy to know what it is right off the bat. On the other hand, if our dv has to be the rest, remember, this is dv we're picking. So there's our u right there. And dv is everything else. So it's my x squared times dx. Then we find the rest of the things. We need to find du and v. So du is just the derivative of the natural log of x times dx. So that's 1 over x times dx. And my v is the antiderivative of x squared. And the anti-power rule, so that's going to be x cubed over 3. I guess I could say these parts together, that part with that part, that's my dv. Yeah.
So if you want to say like your first kind of like instinct is you want to try to do so.
Yes, that is totally 100% correct.
And like the big like key takeaway of the two substitution is if like you find u and the derivative is in the equation, or you can modify that like for constants and stuff.
Right,
Well,
and
that-
I would say, yes, that's generally what we look for. Also, we look for U trapped inside another function, but I'm also gonna say that sometimes when you do a U sub and it's the right choice to do, your derivative doesn't end up showing. Which is unfortunate, but sometimes it's what we have.
Okay. Should we, everyone, like, should I just like always try, like,
You should try, like, yeah, so like, we'll kind of hit some problems where it's, you have to do, so basically, if you have a composition of functions, like a cosine of something terrible, or needed something terrible, and kind of nothing else to multiply it by, often you're stuck with a U sub there, and you can't get out of it. But again, yes, your instinct is correct. We should try U sub first. If it doesn't look like it's gonna work out relatively easily, and you see, and it seems like we could use integration by parts instead, that's what we should usually do. Usually. So here, we're going to rewrite this as, I don't think you actually need to write out this is equal to the ultraviolet super voodoo. Well, you certainly can. I think you can go straight to writing out, though, that it's just going to be what it is in terms of our functions there. So our u is the natural log of x. Our v is x cubed over 3 minus the integral of v, which is x cubed over 3, times du, which is 1 over x dx. The whole point of this process is that this new integral should be easier to deal with. But sometimes that requires that we simplify. So I really want to make sure that when you see this, that you know that you can multiply these together to get an easier function. We definitely cannot anti-differentiate each part separately. If we could, that's what we would have done in the first place. So here we're going to get, excuse me, I'm going to rewrite this as 1/3 times the natural log of x times x cubed. I probably would put the x cubed in front, but too late. Minus, I'm going to pull out the 1/3 constant multiple here, and x cubed divided by x is just x squared. And now it's not terrible at all. We're going to get 1/3 times, let's write it as 1/3 times x cubed times natural log of x, minus 1/3 times the integral of x squared, which is x cubed over 3 plus c. So similar-ish looking integrals, very different methods to do them. Get one more kind of comparing and contrasting here. Oh yeah, that's a good one. So let's say we have, yeah, let's do the antiderivative of the integral of x times cosine of x squared. So what do y'all think? Is the u sub gonna work? Yeah, what's my choice for u here? X squared, because it's inside the cosine and its derivative is practically there. My du is equal to 2x dx, so multiplying both sides by 1/2. My 1/2 du is equal to x times dx. And I can rewrite this integral as, well, the x times dx. That's going to be equal to my 1/2 du. And my cosine of x squared is now going to be cosine of u. We know how to anti-differentiate cosine of u. That's going to be 1/2 sticks around. Antiderivative cosine is positive sine of u. Let's see. And then we end up with 1/2 sine of x squared. Let's see. If you've typically used u substitution and you get your antiderivative looks like something that you could differentiate and end up using the chain rule right away. And we would, right? The derivative sine of x squared is cosine of our stuff times the derivative of our stuff. Whereas in the previous problem, take the derivative here, you'd have to really use the product rule. Right? You've got x cubed times natural log of x. So that's kind of a good thing to think about if you're using these processes. If your answer is the right kind of thing, u sub should lead to a function that looks like you would differentiate with the chain rule. Integration by parts looks like something you should differentiate using the product rule. And again, there might be more to it than just that, but at a very basic level, that's what we should always kind of see. All right, let's compare and contrast this with, yeah, the antiderivative of x squared times cosine of x. Definitely not a u substitution. There is no good choice for u here. So we're going to do integration by parts. And according to my late acronym, I don't have a logarithm, but I do have any power of x. I have x squared. Some other people, by the way, I like to say any power of x. Some other people call that the algebraic term if they're using this acronym. I like to call it any power of x because it feels more descriptive. So we're going to let u equal the any power of x part, which is the x squared. As soon as you've picked your u for integration by parts, I should write integration by parts here. So the u sub. As soon as you, oh yeah, question. 2x and the x squared. Oh, sorry. Yeah, sorry. Sometimes my d's do look like 2's. I apologize. But your integral should always end with a d, whatever your variable is. Yeah, good. Yes. If I had a 2x, I certainly would combine. So as soon as we've written down what our u is, the next thing you should write down is the dv is whatever else is multiplied by what you chose for u to finish off the entire rest of your integral. So everybody write down what dv is. 15 seconds. Right, everybody should have written down the dv is equal to cosine of x times dx. Someone asks, could we have used integration by parts in problem 5? And the answer is definitely not. And the reason we couldn't use integration by parts here is because, I mean, whatever you choose for you, like if you choose this for u, then your dv would have to be this, and we can't actually integrate cosine of x squared. Like literally, is not anti-differentiable. And if you chose that for u and that for dv, then that's going to be worse when you integrate it, and the derivative of cosine of x squared is terrible. So no, typically you can't use. So some problems do require u substitution and integration by parts in sequence, but for some integral, it can only either be solved using one method or the other. You typically couldn't use both methods to solve the same integral. But definitely not. We cannot use integration by parts here. Here, on the other hand, we can. So let's write down the rest of what we're doing. My du is going to be 2x dx. And my v, which is the antiderivative of cosine of x, is sine of x. Let's write down what this is equal to. This is going to be equal to uv minus the integral of v du, which is going to be equal to x squared times sine of x minus the integral of sine of x times 2x dx. And we could pull the 2 out in front, but that's still not going to help us that much because the integral of x times sine of x, something we don't know. It's something that, again, requires integration by parts. So we have to do it again. So now for this new integral, we're going to let u equal 2x. Our dv is going to be sine of x dx. Sorry, it's kind of smashed in there. Our du is going to be 2 dx. And our v, which is the antiderivative of sine, is going to be negative cosine of x. So then this whole thing is going to equal the x squared sine of x is still hanging around, minus the entirety of my new uv minus the integral of v du. So my new uv minus the integral of v du is going to be 2x times negative cosine x. I might write that as negative cosine of x times 2x, just so I don't have to have a weird parentheses around my negative sign. Zoom in a little bit here. And let's do that. And then minus the integral of my v du, which is a negative cosine of x times 2 dx. And now I've gotten to a place where I can actually integrate the thing that's in my integral. Let's do a little bit of rewriting. I'm going to write this as x squared times sine of x. Minus a minus is plus 2x times cosine of x. And then minus a minus is minus the integral, let's put the 2 out in front, minus 2 times the integral of cosine of x dx. And finally, we end up with x squared times sine of x plus 2x times cosine of x. And the antiderivative of cosine is positive sine, so we get minus 2 times sine of x plus c. So sometimes we have to do integration by parts more than once. Yeah. So the first, like here?
Yeah.
So when we're finding du, so, I see what you see. So if I was doing a u substitution, I would be trying to make the thing that du is equal to look like something that was in my integral. But we're not doing a u sub here. So the whole thing here is that whatever du is has to show up exactly as it is. When I'm doing integration by parts, I'm not manipulating any of this. When I'm doing u substitution, I am manipulating this a lot if I need to. So that's why. If you're doing integration by parts, things get to stay as they are. So most time, so I would say for a problem like this, we would often use a method. It's really just a shortcut. How many of you learned, raise your hand if you learned or are familiar with, what's that called? Synthetic division. Like, remember when you might have learned polynomial division back in the day, and then someone might have taught you a shortcut for it. That is not my favorite thing. I don't like it at all, really. I've learned to kind of be okay with it, called synthetic division, where you're basically doing the same process, but you're just writing down less stuff, but it's meant to be faster. Well, the same kind of thing is applicable for 3 types of integrals that require repeated integration by parts. So let me show you how we could have done this problem without writing down quite so much. And then I'll talk about what other kind of problems we could use this for. So here's the same problem using the tabular version, which is what this is called, the tabular method of integration by parts. It's still integration by parts, you're just writing down less stuff. So instead of doing u equal to x squared and dv equal to cosine of x dx, instead what we're going to do is the following. We're going to write u, and then we're going to make a column below it. So, and we're going to start with x squared. And for dv, we're going to write cosine of x, but in a column below it. And we're going to just leave off the dx's. And then in the u column, we're going to find all the derivatives of the thing that we said u was equal to. So the derivative of x squared is 2x. The derivative of 2x is 2. The derivative of 2 is 0. Yes, you need to go all the way to 0. In the dv column, we're going to find the antiderivatives, and we're going to go at the same number of rows or entries. So the antiderivative of cosine of x is sine of x. The antiderivative of sine of x is negative cosine of x. The antiderivative of negative cosine of x is negative sine of x. And then you get this pattern of, well, so let me point out, what we really have here is we have u times v. And then we have minus the integral of v du. But then the new integral part, we use integration parts again, we get a minus, and it becomes plus the integral of your new v du, and so on and so on and so on. So you get this plus, minus, plus, minus, plus, minus pattern. It always starts off with plus, and then it just keeps alternating. So to find our answer here, the antiderivative of x squared times cosine of x dx is going to be equal to plus x squared times sine of x minus 2x times negative cosine of x plus 2 times negative sine of x plus c, and then we should rewrite it as x squared times sine of x plus 2x times cosine of x minus 2 times sine of x plus c. And if we double check back here, Looks pretty good. Looks the same. So people should be okay with you using this method. It's not like you're cheating or doing anything wrong. It's just an abbreviated version of doing what we're already doing. So when can you use this, or for what intervals will this work for? 3 types. You have to have an integral where the u thing you are choosing is x to a positive integer power. So that eventually, if you take enough derivatives of your u, you will get down to 0. And your dv choice has to be something that if you keep integrating it repeatedly, it doesn't get terrible. And there's only 3 functions that'll do that for us. Cosine is one of them. What's another one? Sine. And what's another one? What's another function that you can anti-differentiate and it basically doesn't change at all? E to the x. Those are the 3 things. So the candidates for tabular integration are, I'm gonna write this slightly differently, x to a power, where the power is a positive integer, and you can either have e to the some constant times x, or you can have x to a power times cosine of some constant times x, or you can have x to a power times sine of some constant times x. Those are the 3 types of things that we can use tabular integration for. There are other integrals that will require integration by parts multiple times that we can't use tabular for. But these 3 ones specifically, you can. So let's do one more example of this and then we'll move along. Time is fleeting. So let's say we wanted to find the integral of x to the 3rd times e to the negative 2x dx. This is one of those instances where it's really vital that we are just comfortable saying, oh, I know the antiderivative of e to the negative 2x is e to the negative 2x divided by negative 2. So, tabular time. We're going to let u be what? X to the 3rd. And dv is the rest, except we're not going to write the dx part. So dv is going to be e to the negative 2x. Differentiate u, anti-differentiate dv. So find all your derivatives of u. I try to give myself some vertical space here because sometimes the antiderivatives take a little bit more space. So my derivatives are 3x squared, and then 6x, and then 6, and then 0. My antiderivatives are going to be e to the negative 2x divided by negative 2, and then e to the negative 2x divided by positive 4, because I'm dividing by another negative 2, and then e to the negative 2x divided by negative 8, and then e to the negative 2x divided by positive 16. So every time I anti-differentiate e to the negative 2x, I just end up dividing by another negative 2. And then we go down diagonally from upper left to lower right. But it's important to make sure your things are kind of aligned appropriately. And then it's plus, minus, plus, minus. So here it looks like everything's actually going to turn out to be negative, because it's going to be x cubed times e to the negative 2x divided by negative 2. And then negative 3x squared times e to the negative 2x divided by 4. So I was going to write this out. I'd say this is equal to negative 1/2 x cubed e to the negative 2x minus 3/4 x squared e to the negative 2x minus 6/8 is 3/4 x e to the negative 2x minus 6/16 is 3/8 e to the negative 2x plus c. That's a whole lot less time than it would take to actually write out doing integration by parts 3 whole times. Because that's how many times you'd have to do it here if you were going to do it the long way. And if you want, sometime in office hours, I'd be happy to show it to you the long way. All right. What other things? There's so many things with integration by parts to say. let's look at, yeah, let's look at one more kind of standard tricky thing. Oh, where'd you go? Let me look over here real quick. Not you, not you. Oh, that's a good one too. So many good problems. I know. Is it always, yeah, yes, it is always plus minus plus minus. You always start with a plus and then it changes minus plus minus plus minus every time. Yeah, let's look at that one. Sure, that's a classic. So here's a fun one. You can tell by the tone of my voice. Let's look at the integral of e to the 3x times sine of x. Yeah, we'll torture ourselves with this. So this is the type of problem, specifically e to the something times x times either sine of x or e to the something times x times cosine of x, where this process that we're about to use is the only way to do it. So this integral requires special attention. And definitely, I've seen, at least in Dedella's class, this type of thing. So I think you've been hit with like just e to the x times sine of x, or maybe e to the x times cosine of x. Or it might have actually happened after you already did the u sub. Like I think you see this type of thing when you're doing the integral of sine of natural log of x. We'll talk about that in a second. So here, we're going to do our usual integration by parts. So we're going to let u equal sine of x, and dv is the rest. We'll mention here, so I've made my usual choice based on my, again, my late acronym. I didn't have a log, I didn't have any power of x, so I let u equal the trig thing. And then my dv is the exponential thing. My du here is cosine of x times dx. And my v is the antiderivative of e to the 3x, which is e to the 3x divided by 3. So then we're going to write this out. We're going to say that my integral of e to the 3x times sine of x dx is equal to u times v, just sine of x times e to the 3x over 3, minus the integral of v du, which is e to the 3x over 3 times cosine of x dx. And choices here. Just trying to think about one thing. Oh, it's fine. So now we're going to do integration parts again. And I'm going to let my u equal cosine of x, my dv be my e to the 3x over 3 dx. My du is going to be negative sine of x. And my v is going to be the antiderivative of e to the 3x over 3 is going to be e to the 3x divided by 3 times 3, which is 9. So then, be writing this is going to be equal to, I still have this front part here, sine of x times e to the 3x over 3 minus the entirety of my uv minus the integral of v du. So it's going to be minus this u times this v. So cosine of x times e to the 3x over 9 minus the integral of v du, which is e to the 3x over 9. Oh, I forgot the dx on my du here. Times negative sine of x dx. So I don't really want to write a negative sign of x there, so I'm going to put the minus sign out in front and say a minus is a plus sine of x dx. The totally valid thing to do. Then let's write the whole thing out. So on the left-hand side, I still have my original integral. So I have the integral of e to the 3x sine of x dx. There is a reason I'm writing this first part. It's not just because I want to. Equal to, I've got this part here, which is sine of x times sine of x times e to the 3x over 3 minus cosine of x times e to the 3x over 9, and then a minus this integral here. I'm going to write as minus, I'm going to bring out the 1/9, the integral of e to the 3x times sine of x dx. And what you might observe is that we've gotten back to the integral we started with. I was trying to find the integral of e to the 3x sine of x, and I've gotten back to the integral of e to the 3x times sine of x. And so what do? We add it to both sides. I'm going to add 1/9 the integral of e to the 3x times sine of x dx. And if you have a whole something and add a 1/9 of that something, well, one of this integral plus 1/9 of that integral is 9/9 plus 1/9 is 10/9 of that integral. Yeah.
Anyway, you could like separate the 1/9 and just add the integral and then just have 1/9 from the end, or no?
No, it is 1/9 times it. So here we have, or you could think about like factoring out the integral here, but essentially you have 1 plus 1/9. So you have 10/9 of the integral you're trying to find. E to the 3x times sine of x dx equal to sine of x times e to the 3x over 3 minus cosine of x times e to the 3x over 9. And I really wish I had just a little bit more space here, but I think I have to use another piece of paper. So then solving this, we multiply both sides by 9/10, and we get that the integral of e to the 3x divided by times sine of x dx is equal to 9/10 times sine of x times e to the 3x over 3 minus cosine of x times e to the 3x over 9 plus c. Kind of wild. So whenever you see an e to the x times sine of x, or an e to the x times cosine of x, or an e to the 2x times sine of x, or an e to the negative 5x times cosine x, or an e to the something times x times either sine or cosine, this is the way to do it. Where you do integration by parts twice, you end up with essentially the same thing you started with integrating. You add it back over to the other side, and then you multiply both sides by the reciprocal of whatever that coefficient is to isolate your thing. It's kind of ugly. Okay, let's look at a few other problems here. Yeah. So the thing about integration by parts is it's just one of the many methods we will have in our toolkit of integration tools. Very linguistically sound there. Anyway, but let's say we had something like the antiderivative of, yeah, let's do that one. Let's do sine of the square root of x. Here's a problem that doesn't look great. It doesn't really look like I could use integration by parts. And in fact, I shouldn't even be thinking about integration by parts first. I should really be thinking about u substitution, right? I should follow my own rules. I've got a mixture of things. I've got a sine of a root x. That's still technically a mixture, I guess. I would try u sub with u equal to the square root of x. And immediately I'm disappointed by this because if my u is the square root of x, which is x to the 1/2, my du is 1/2 x to the negative 1/2 dx. Or as I would prefer to write it, my du is 1 over 2 root x dx. And I'm disappointed because I really don't have that. Like not at all in the least. Problem here is I'm kind of stuck. Integration by parts is not going to help me. If I tried to do integration by parts, I could pick u equal to sine of root x, and my dv would be dx. Could that work? No, that's not going to work. It's not an integration by parts problem. So here's the thing. When you're kind of stuck with something like this and you don't really have a good other option, but your du is terrible, let me go in a different direction. So instead of doing this part here, well, actually, I'm going to leave that there for a second. So there's actually kind of two ways to deal with this. What we usually do is we take our u equal to root x and we solve for x. So in this case, to solve for x, what do I need to do to both sides? Yeah, I mean, u squared equal to x. And I'm going to differentiate both sides with respect to u. So I'm going to essentially say is, I'm actually going to write it as x equal to u squared, and then dx du, the derivative of x with respect to u. Well, what's the derivative of u squared? Du. Or if you prefer, and I do prefer, dx equals 2u times du. And I can take that and replace my dx with that. Let me work up my choices, but fine. So I'm going to rewrite this integral as, so my dx is going to get replaced with 2u du. And my sine of root x, well, u is equal to root x, so that's going to be sine of u. And now I'm really, really displeased. Well, not displeased, but I'm fine. I can write this as 2 times the integral of u times sine of u. The reason I'm unhappy is because now I have to use integration by parts. I'm not unhappy about that. I'm happy that I've already used the variable u. I don't love that I've used up my u. So what I would often do in this case is go back and change all my u's to a different letter. But that feels kind of like terrible. So what people often do when they've already used u and they have to do integration by parts next is they, instead of doing u in dv, they use w in dv. That's another. So I'm going to do integration by parts now. Do I have enough room? Maybe. So I'm going to let w, so w standing in for u. So w is going to be the algebraic thing. So w is going to equal u. And my dv is going to be my sine of u du. My dw is going to be the derivative of u, which is just 1 du. And my v is going to be the antiderivative sine of u, which is negative cosine of u. Running out of room. So then, instead of doing uv minus the integral of v du, we're going to do wv minus the integral of v dw. And yeah, I can't try to squeeze it in here, and I shouldn't is the better thing to say here. So this integral, 2 times the integral of u times sine of u, is going to be equal to 2 times my wv minus my integral of v dw. And then I'm going to replace the w's and the v's with what they're equal to in terms of u. That's going to be 2 times wv is u times negative cosine of u, or negative u times cosine of u. My v dw is negative cosine of u times du. Great, we know how to integrate cosine. So then we're going to get 2 times negative u times cosine of u plus the antiderivative of cosine is sine. And then, sorry, you can't quite see that. We have to go back and plug in what u was equal to in the first place, which was the square root of x. So then we're going to get that the antiderivative of sine of root x is equal to 2 times negative root x cosine of root x plus sine of root x plus c. And if you took the time to take the derivative of this, it would end up equaling sine of root x. So sometimes you have to do a u sub combined with integration by parts. A problem that I'm not going to do fully, but I will start off, is this problem. I think it's sine of natural log of x. Kind of works the same way. You don't really have a lot of choices here, so we end up letting u equal the insides. And then your du is not helpful. Well, it's not entirely not helpful. So there's a couple ways to see this. I personally like to do it the way I just did it. Whereas I would take my, since this is not helpful, I'm going to take my u equal to natural log of x. I'm going to solve for x. So I'm going to e both sides. I'm going to get e to the u equal to e to the natural log of x, which is just x. I'm going to differentiate both sides. The derivative of e to the u is e to the u times du. The derivative of x is 1 times dx. And then I can say that dx is equal to e to the u times du. I skipped a step here, right? Last time I said x was equal to whatever, And then dx du, the derivative of x with respect to u is just equal to the derivative of that, which happens to be the same thing as it was. And then it brought the du over. I'm kind of skipping that stuff. Basically, when you differentiate the side with u on it, you get the derivative times du. When you differentiate the side with x on it, you get the derivative times dx. And then if I start replacing things here, this is going to be equal to, well, dx is e to the u times du. Sine of natural log of x is sine of u. And then you have one of those problems where it's sine of x times e to the x. And you have to do integration by parts twice. And then you end up with the integral you started with, and you have to add it back over to the other side and then divide by whatever the coefficient is. It's terrible. Kind of a lot, but it's doable. The thing I was saying though is this here is technically not helpful. You could instead, if you prefer, say, oh, well, look, if I solve for x equal to e to the u, you can plug that in here and say that, sorry, I've left myself not a lot of room here. You can say that du is equal to 1 over e to the u times dx, or e to the u times du is equal to dx. You can get to this place a different way. In fact, I could have done that in the previous problem as well. I could have said up here, instead of saying here, dx equals 2u du this way, I could have looked back here and said, oh, look, u is equal to root x. So du is really 1 over 2 times u times dx, and then 2 times u times du is equal to dx. I don't like doing it this way, because usually you have to think hard. It's almost always more straightforward and easy to solve for x, and then just take the derivative of both sides and get dx equal to whatever. If you're doing it this way, you have to work harder to get dx on its own, I think. Okay, let's look at another problem. Oh gosh, time's always running away from me. So let's look at the integral of where'd you go? Oh, you got so many things. Yeah. X to the 5th, e to the x squared. All right. So integration by parts, or you sum? Well, here's the thing. For integration by parts, I don't see a good choice for dv. Right, like if I let u equal x to the 5th, my dv would have to be e to the x squared dx, and fun fact, e to the x squared is impossible to anti-differentiate. Literally not possible. You cannot find the antiderivative. So it's never a good choice for dv because we don't know its antiderivative, doesn't exist. There are other ways to do this, and but the easier path here is to do a u sub first. So since I know that I'm going to do a u sub and then I'm going to do integration by parts after that, I'm not going to use the letter u for my u sub. So I would love to save u for my integration by parts. So instead of saying u equals x squared, I'm going to say t equals x squared, or pick whatever letter you like. And then my dt is equal to 2x dx. Oh, I have an x times dx. I actually have more than one x times dx, but I have a lot of x's. I can break out one of them. So my 1/2 dt is equal to x times dx. I'm going to rewrite my integral as the integral of, I'm going to pull out one of the x's from x to the 5th. So I have x to the 4th times e to the x squared times x times dx. And now we're ready to rewrite this. There's your 1/2 dt. X squared. There's your u. Sorry, my t. I called it t, not u. But then I have some x's left over. And when you have x's left over in a u sub, we do a back substitution. So t is equal to x squared. I have an x to the 4th. So t squared is equal to x squared squared. So t squared is equal to x to the 4th. So I'm going to end up with this being t squared. So I'm going to rewrite this as the integral of t squared times e to the t times 1/2 dt. Or more nicely written as 1/2 the integral of t squared e to the t dt. And now I have to use integration by parts twice. but I could use tabular. And I should use tabular. So I'm gonna use tabular. My u is gonna be t squared. Sorry, I wrote it the wrong way. My u is gonna be t squared. Its derivatives are 2t, t, and 0. My dv is nice. It's gonna be e to the t. The antiderivatives are always just e to the t. So I'm gonna get plus that, minus that, plus that. Is gonna be equaling 1/2 t squared times e to the t minus 2t e to the t plus 2e to the t plus c. And then we have to go back and plug back in that t is equal to x squared. So we're really getting 1/2 times x squared squared e to the x squared minus 2x squared e to the x squared plus 2 e to the x squared plus c. Yeah.
I'm confused about the t squared, like, when should we do that?
So fair enough. So I had dealt with this part and I had dealt with this part, but I still have this x to the 4th left over. So what I did was I looked back at my choice for my u sub and said, oh, how can I make this side look like x to the 4th? Well, I squared it, but I can't just square one side of the equation. I have to square both sides. So I squared both sides and said, oh, x squared squared, which is x to the 4th, is equal to t squared. So that's how I was able to replace that one. Let's look, yeah. Well, I guess we're not gonna get the partial fractions today. Oh well. We'll talk about that next time. So let's look at one more problem like this. Let's say we want to do the integral of, oh yeah, there was a good one there. Where'd you go? Sorry, I had one all teed up here. I thought I could. It's fine, I can make one up. Let's say we have, sure. Sorry, 1 second. Takes a minute. Yeah. X to the 7th times cosine of x cubed dx. Yeah, that'll work out. That'll work out. X to the 4th. Cosine of x to the 4th. Sorry. That'll work out just fine. So again, I'm gonna go with a u sub here because I don't actually have the ability to use integration by parts. So I pick u equal to x to the 7th and integration by parts. My dv would be cosine of x to the 4th, and that is not something we know how to anti-differentiate. Again, it's probably actually impossible. So I'm going to do a u sub. I'm going to let u equal the stuff inside the function there, x to the 4th. Just in case I forgot, for those of you on the Zoom here, here's the attendance form one more time. My du is going to be 4x cubed dx. And you know what? I'll do this one a slightly different way than I have been. Instead of doing it how I like to do it, which is say 1/4 du equals x cubed dx, I'm just going to isolate the dx here. Some people like doing it that way instead. So instead, we're going to say du divided by 4x cubed is equal to just dx. So if you want to do it this way, that's fine. And if you do it this way, I recommend only changing that part first. So I'm going to rewrite my integral as the integral of x to the 7th times cosine of x to the 4th times du over 4x cubed. And then I want to cancel the x cubed as soon as I can. Well, x to the 7th divided by x cubed is going to leave me with an x to the 4th. So what I have now is the integral of x to the 4th times cosine of x to the 4th times du over 4. And now I can finish off my u sub and replace my x to the 4th with u. So I have a cosine of u du. Oh, look, I have another x to the 4th. Well, that can be u as well. And now we have to use integration by parts. I think these problems are kind of hard, no lie, but I also can see that the Dell is asking problems like this. So, right, a lot of problems similar to this are on his practice exam. So you should practice them. So, how much time we got? Yeah, we got enough time. So we're gonna finish this off since I mistakenly, not mistakenly, since I used up my U already. I guess I'll do my integration parts with letting W equal U and dV equal cosine of U du. And then my dW is 1 times du. And my V is the antiderivative of cosine of U, which is sine of U. So I'm going to rewrite this as 1/4 times my WV, which is U times sine of U, minus the integral of my V dW, which is sine of U du. And then we're going to get it. It's going to be 1/4 U times sine of U minus the integral of sine of U is plus cosine of U. Plus C, and then finally replace your U with what it's equal to, which is x to the 4th, and we get 1/4 times x to the 4th sine of x to the 4th plus cosine of x to the 4th. Let's see. Okay, I got 4 minutes, say a couple things. Thing one, I posted an announcement this morning. Tomorrow from 3:10 to 4:30 in this room, we'll have a derivative review. So I know some few people ask me in the reflections, like I could really use some derivative review, and that's something we actually plan on doing. So tomorrow here, 3:10 to 4:30, derivative review. I will record it. You can come via Zoom if you want to, or you can come in person. And then Thursday, not tomorrow, we will talk about partial fractions, but just as a lead up to partial fractions, let's do one example. I'm also aware that the Dell has an exam on Friday. Unfortunately, I feel like we have to just cover material, so you should practice. He gave a practice test, which has a lot of hard problems on it. You should do them. I'm happy to help with them. Come to office hours, I'm happy to talk about them, but there's some interesting stuff on there. So let's look at one partial fractions kind of deal. So partial fractions, what does that even mean? Well, if you're trying to integrate something like 2x plus 1 over x squared, let's be careful here, x squared plus 4x plus 3, almost a perfect U sub. In fact, when you do partial fractions, before you do partial fractions, you should look out for a U sub. Here, I might think about a U sub for a second. If I let U equal the denominator, my du is 2x plus 4 dx. Ah, so close. One at the top was a plus 4 instead of a plus 1 to be perfect. But it's not perfect, so it doesn't work. So if we can't do that, then we hope we can do partial fractions, which requires a few things to be true. You have to be integrating a rational function, VR, to polynomial divided by polynomial. The degree on top has to be strictly less than the degree on the bottom. If the degree on top is equal to or bigger, we first have to do polynomial division. And then if those two things are true, the denominator also has to factor. So we're going to rewrite this as the integral of 2x plus 1 over x plus 3 times x plus 1. And then our job is to write this fraction, 2x plus 1 over x plus 3 times x plus 1, as the sum of two fractions with less complicated denominators. Specifically, the denominators that are the factors, x plus 3 and x plus 1. And there are some constants we don't know that if we pick the right constants, these two things, when we get a common denominator, will actually add up to that. The fast way of solving this is to multiply both sides by the common denominator, which is x plus 3 times x plus 1. When we multiply this by that, you're always just going to get what's in the numerator. And the whole point of doing this part is just to get rid of denominators. When you multiply x plus 3 times x plus 1 by that, the x plus 3's cancel, and you get a times x plus 1. And when you multiply this times that, you get b times x plus 3. There's lots of ways of going about solving this, but the easiest way to do this is to use what I refer to as the convenient values of x. The values of x that make one or more of these things equal to 0. So if we pick x equal to -1, and plug it in, well, we get 2 times -1 plus 1 equal to a times 0 plus b times 2. That's -2 plus 1, so -1 is equal to 2 times b. So b is equal to -1/2. And if we let x equal -3, well, then we're going to get 2 times -3 plus 1 equal to a times -3 plus 1 is -2 plus b times 0. Or -6 plus 1, -5 equal to -2a. So a is equal to 5/2. And then we get to say, oh, this integral is equal to the integral of 5/2 over x plus 3 minus 1/2 over x plus 1. And those things are much, much, much easier to integrate. Bless you. That's going to be 5/2 times the natural log of the absolute value of x plus 3 minus 1/2 times the natural log of the absolute value of x plus 1 plus c. There's a quick example of partial fractions. We will talk more about that on Thursday, but I wanted to give you a fast one just so you can see one example of it. All right, I have office hours over in C class, and then later this afternoon in drop-in, I'll be around. Is there a trick to know how to factor that fast? I was looking, well, I really started with this to multiply it out, but I'm looking for numbers that multiply to 3 and add up to 4, which are 1 and 3. And do you fill out the attendance form if you didn't already?